We'll now discuss the third sorting algorithm, which is called insertion sort. Now, I should mention first that out of all the three basic sorting algorithms, insertion sort is actually the fastest. With that said, it's still O of n squared time. It's just if you actually timed it, it is faster than the others. Here's the idea, and I will warn you that it may be a little confusing at first, but it'll make more sense as we see examples in the code. So let's say we're at some iteration p, where p can be anywhere between 1 and n minus 1. What we have here is we're going to ensure that all the elements from A0 to AP are sorted at that iteration. We'll see how we get that in just a little bit. So that means that we can just simply assume that everything from AP and to the left of our array is completely sorted, but that means everything from AP plus 1 onward is unsorted. So what we're going to do is we're going to remove the first unsorted element, which is at AP plus 1. So imagine we take that out. And then we're going to move that down the array towards A0. And then we're going to find the spot within the sorted portion of the array where we would put in AP plus 1. We put it in the correct spot such that A0 to AP plus 1 is now sorted. So this is actually similar to how you would sort cards in your hand during a card game. So how would you normally do that? You would take one card out, and then you would move it down and just insert it into the correct spot. We're going to do the same thing here, except we're dealing with array elements instead of cards. So we're going to go back to our same example that we did for bubble sort and selection sort and see how we would do this for insertion sort. We'll start with position p equals 1. We don't have to worry about position 0 because if it's just one element, it's already sorted. So that's why we're going to start at position 1. We then remove the value from the array, and then we're going to move down until 8 is in the correct spot. Now, this is just for visual purposes. In the memory, we wouldn't actually remove the element from the array. We would just copy it somewhere else. But I'm removing it here just so you can visually see what's going on. So in order to move down the array, we have to shift the other elements up a spot. So here, to move down to position 0, we have to shift the element that's at position 0 and move it to position 1. We then see that we're at the end of the array. We can't go any farther down, so this must be the correct spot. So then we put 8 at A0. And so what we see here at this point, that positions A0 and A1 are now sorted. We'll now do the next iteration where we look at position P, where P equals 2. So we'll remove 64 from our array. Now normally we would move it down the array, but in this particular case we notice that there's no point in moving it down because 34 is less than 64. So that means the 64 was already in the correct spot. So we're just going to insert it back at position 2. So now we have positions A0 to A2 sorted. We'll do the next iteration where our position is now at 3. So we remove 51 from our array. And since 51 is less than 64, which was the value at A2, we need to shift down one place, so we move the 64 to A3. And since 51 is greater than 34, this has to be the correct spot for 51, so we're going to put 51 at A2. We'll now do the next iteration where we look at position 4. So just notice that from A0 to A3, everything is sorted. We remove 32 from our list. Since 32 is less than 64, we need to shift the 64 over one place, so we move it over to A4. 32 is also less than 51, so we need to move the 51 over to A3. 32 is also less than 34, so we have to shift the 34 over to A2. And then finally we see that 32 is greater than 8, so we don't shift anything anymore. We know that A1 is the correct place for 32, so we'll put 32 at that spot. We'll now do the last iteration, which will be at position 5. So we need to remove 21 from our array. 21 is less than 64, so we need to shift the 64 over to A5. 21 is also less than 51, so we need to move the 51 over to A4. 21 is less than 34, so we need to move the 34 from A2 to A3. 21 is also less than 32, so we need to move the 32 from A1 to A2. And then finally, we see that 21 is greater than 8, greater than A0, so that means A1 is the correct spot for 21, so we're going to insert the 21 there, and now the entire array is sorted. Here is our code for insertion sort. So I want to mention a couple things about this code. So our for loop is our position P, so we start at position 1 and we go up to not including position N. And then the first line inside the body of this loop is how we remove an element. So this line right here. So like I said before, we're not actually removing the element. We store the value of that element into some temporary variable. And then the for loop that comes afterwards does the bulk of the work for us. So we start at position P and we move towards the beginning of the array, and we're doing two checks. We first check that j is greater than 0, so this is just checking to make sure we're not at the end of the array. And then we're checking aj minus 1 is greater than temp. So this lets us know, do we need to shift anything else onward? If this ever becomes false, then we know that we're in the correct spot of our sorted portion of the array. So we see that the body of this for loop just takes the value that's at aj minus 1 and stores it into aj. So that's how we are moving things over. And then once we finally get the spot where we need to add our element, then we put temp into aj. So what we see here is as we move down the array, we're technically opening a gap, and we keep moving that gap onward, even though we don't actually have a gap in our memory, but that's the way we can think of it. And we keep moving this gap down until we get to the spot where we're supposed to insert temp. So now let's show why this algorithm takes O of n squared time. So our outer for loop is going to have O of n iterations. P starts at 1 and goes up to n minus 1, so that's O of n iterations. And then the number of comparisons in the inner for loop is at most P plus 1 times, because we start at position P and we go down until we either get to the end of the array or until we find the correct spot. So we do this for each value of P. So how large can P become? Well, P is O of n. As worst case scenario, we're moving pretty much all the way down the end of the array every single time. That can happen. So that means the inner for loop has O of n iterations. And since we have pretty much a nested for loop where each one takes O of n time, the total running time of this algorithm is O of n squared.